and welcome to FusionEPtalks, a student-led webinar platform for sharing knowledge about nuclear fusion science and engineering. I'm Ekaterina, and I would like to introduce our speaker today, who is Boeyaert, who will be speaking about SOLPS-ITER studies of neon seeding in East Tokamak. After obtaining his master's in mechanical engineering in 2016, Dieter started exploring the wonderful world of fusion during his PhD. And in his PhD, which he started in the Munich Centrum in Germany as a part of UCN collaboration framework of Eurofusion, he focused on examining methods to decrease the power and particle exhaust towards the divertors during Tokamak operation. And neon seeding seems promising for this purpose. As neon seeding experiments are difficult to maintain in European tokamaks, neon seeding experiments were performed on the East Tokamak in China, and the discharges further analyzed with SOLPS-ITER code. These SOLPS-ITER simulations were performed in collaboration with University of Leuven, from where Dieter obtained his PhD degree in October 2021. And currently he is working as a postdoctoral researcher at the University of Wisconsin-Madison, where he studies the neutral pressures in Wandelstein 7X with EMC3 EIRENE. So without further delay, I give the floor to Dieter.
Okay, thank you very much, Ekaterina, for the nice introduction. Hello everyone. As introduced, I'm Dieter Boeyaert, and I'm presenting today to you SOLPS-ITER studies of neon seeding in East. And the first question that we have, of course, when we are looking to such studies, then the question is like, why do we want to do neon seeding? What's basically the goal that we want to achieve? And for that, we have to look to a simplified picture of the plasma edge in tokamaks. And when we look to such a simplified picture, we can see that the power that we have from the core, where our fusion process is taking place, is traveling to the edge around outer midplane and then going further down to the divertor targets, where we will finally have the interaction of the still kind of hot plasma with the material of the wall. And in order to avoid that this wall material that we use for these divertor targets get damaged, we want that our plasma is still cooling down significantly before it reaches the targets. And here on the right, you can see on this picture like the different physical mechanisms which can play a role in decreasing this temperature. So there will be conduction of the heat, there can be radiation, ionization, neutral friction, and recombination. And depending on which of these processes is playing a role, we can divide the regimes that we have in three main classes. And the first one is that when we have a limited heat loss between upstream, so between here when our power is coming from the core, and what we have basically at the diverter targets. In this case, only the sheet which is followed really in front of the diverter targets is playing a role. And that's why this regime is called like the sheet limited regime. It might also be that we have a little bit more luck and that also the conduction is playing already an important role. And in that way, we are in the conduction limited regime. And when we still have more luck, that is that all these different mechanisms are contributing to the heat loss. And then we are in what we call the detached regime. And that is basically what we want to achieve to decrease the power and particle exhaust towards the diverter targets. And there are different mechanisms for it. And I was looking during my PhD time to two of these mechanisms. And that is the use of neon seeding, so an impurity which will radiate and so increase our radiation. And that was also the use of a double null configuration. So here on this picture on the right, you can see that we have here like one X point, but you can also increase this number of X points. And when you have one at the bottom of your tokamak and one at the top of your tokamak, we call this a double null configuration. And it might be that this also is an advantage for power and particle exhaust. So that is what we want to study. Where I was studying it, I was studying that at the East Tokamak, which is located in China. And I was doing that through experiments, which I performed over there in 2019, and with SOLPS-ITER simulations, to what I will come later on. But first, I will start with the experiments that we can see like, okay, what are the observations that we made with them, and can we already draw strong conclusions from them? And here you can see the most important parameters which we had from these experiments. First of all, you have to know that it was not really possible to do a real double null configuration. On the previous slide, I told you that that was the initial goal, but due to technical constraints of the East Tokamak, it was only possible to what they call a disconnected double null configuration, which means that you still have one X point, which is at East mostly the upper X point, so here at the top, and that you also have a lower X point, but that the separatrix between them is not connected, but there is a separation of, in this case, 1.5 centimeters between here the solid line and the dotted line. Unfortunately, it came out that this, when you can do it in this kind of configuration, in this disconnected double null, that this has no beneficial effect on the plasma behavior. As you can see here, for instance, for the radiated power, by comparing the green and the red line, there you can see that there is barely any change. And also when you look here to the right, where you see the profiles at the upper outer target made with the divertor Lamier probes, you can see that the green and the red dots are also really similar. Luckily, there is a strong influence of the neon seeding. That was a second technique which we tested by then. And here you can see that, first of all, the radiation is increasing a lot, which means that more of the power is radiated, what we want. And also you can see that there was a strong effect on the divertor target profiles. You can see that there is an increase in the particle flux, there is a decrease in the temperature, and there is also a strong decrease in the heat flux. Now, for detachment, ideally, we would have a decrease of all three parameters. But there is one important point that we have to keep in mind, and that is that during the neon seeding, there was also an increase in deuterium injection. This had to do with the fact that it was not possible to inject pure neon, but it could only be done when we did the experiments in a mixture of 50% neon and 50% deuterium. And this deuterium can, of course, also then increase the flux that we have towards our diverter targets. So from only the experimental data, it's difficult to draw a really strong conclusion. And that is then where simulations come in the picture, as they can help us to understand which plasma physics is happening and to also decide if we are now on the good track of reaching detachment or not really. And for that, I'm using the SOLPS-ITER code. For those who don't know the SOLPS-ITER code, the SOLPS-ITER code is designed to model the plasma edge and solve over there the Brzezinski equations. And it is a coupling between two codes, the B2.5 code, which is actually solving these Brzezinski equations, and it is the EIRENE code. The EIRENE code is a neutral code, which is solving the Boltzmann equations, and it can be used to foresee the source terms in this B2.5 code. And that is for what we used it, and with what we tried to model the experiments which I showed before. So to start with this modeling, I first started to model the unseeded reference discharge. So that means the red dots on the previous slide. And there it was possible, after scanning the transport which we have in this code, to have a reasonable agreement between simulations and experiments around the outer midplane. However, as you can see here at the right, the agreement between experiments and simulations at the upper outer target is still kind of poor. You can see the temperature profile is matched in a reasonable way, but all the other profiles are still far off from what we see from the experiments. And then the question is like, what is causing this mismatch? This might be that is due to numerical errors, because SOLPS-ITER is a numerical code, which also means that you introduce numerical errors. So that's the first thing to what I will look to. Secondly, I will do some sensitivity studies, because not all the input parameters we know exactly. On these experimental data, there is always an error bar. And for instance, the upstream separatrix density, that is one of the parameters which is fixed during my simulations. But it also means when this is changing a little bit, that can have a big influence also on what is happening at the target profiles. So that's the second thing to which I will look to I will look to together with you. And then the third thing is including drift effects. So standard in the SOLPS-ITER code, you have 4 equations which are solved. That is, you look to the particle balance, you look to the momentum balance, and you look to the energy equations for ions and electrons. But you still have your current equations, in which the drift effects are included. And by default, this is not solved in SOLPS-ITER, but it is possible to activate that. And that is then the third thing to what I will present today. But first I will start with a numerical error analysis. And then the question is like, which kind of numerical errors we have present in a SOLPS-ITER simulation. On the right here, you can see the grids which are used in such a simulation, which is in blue, the EIRENE grid, and in red, the B2.5 grid on which the Brzezinski equations and so the plasma is solved. Now, you can see that these grids, yeah, they are finite because you cannot make an infinite small grid. You have at one point to decide this is the one that I can do. But because they are finite, you will also have what we call the discretization error, because you discretize your entire domain on which you want to solve your Brzezinski equations. It turned out that this discretization error is mainly caused by the B2.5 grid, so by the red one. So therefore, I will show in one of the next slides how we evaluate the so-called discretization error. A second error contribution will come due to the fact that we are dealing also with a Monte Carlo code. So the EIRENE code is a Monte Carlo code, which means that you are following particles where they are going. And by following their trajectory, you will extract the information about the neutrals. But you can only follow a limited amount of particles. So also this limited amount will again introduce an error. And that is what we call the bias error. And we study it here as what we call the bias, which is a combination of this bias error and the incomplete convergence. The third error that we will have, that is also due to this Monte Carlo code, and that is because such a Monte Carlo code will also introduce noise. And this noise that will cause a statistical error. And this is normally one of the largest error contributions in codes like SOLPS-ITER, but by applying the so-called SOLPS-ITER averaging, which was developed in Leuven by a previous PhD student by Ghoos. And there you basically say, to say it in really easy terms, you just do not only one simulations, but really a lot of simulations which are converged. So for instance, I did 45,000 simulation steps, and the final plasma profiles that you take is just the average over all these 45,000 iteration steps. And by applying this SOLPS-ITER averaging them, it was possible to keep these estimated statistical errors below 0.5%. So therefore, these statistical errors are really small, and I will ignore them during the rest of the talk. Now, how can we then find the how big are our discretization error and our bias? For that, I'm using what they call the Richardson extrapolation. And for the people who don't know exactly what Richardson extrapolation is, I have here on this slide a short explanation for it. So you basically say like, okay, I have, let's say, two grids on which I solve my solution, which is here a coarse one, and it's here a finer one. And now you say the solution for any plasma parameter that I can have on one of these grids, F, is the exact solution plus an error contribution. And this error contribution will depend on the grid size that I have. So it will be here linear, then quadratical, and so on. So if we now assume that we have a second order of convergence, which would mean that our G1 is 0, and we then note in this format the outcome of our solution on our refined grid as F1 and our coarser grid as F2, then we can rewrite our exact solution as a combination of F1 and a second term, which is an estimate for our discretization error. And this is basically what they call the Richardson extrapolation. I have now explained it here for the discretization error, as you can see that easily, as it's easier to visualize as you have here grids to see, but you can also do that for the bias by just changing the amount of Monte Carlo particles that you involve in your simulation. And I will first start with this bias on my simulations to basically study what is happening. And by applying this Richardson extrapolation, it is possible to basically make error bars on the simulations. And that these you can see here on the plots for the upper outer target and for the upper inner target. And you can see that at the upper outer target, they are, especially for the temperature and for the heat flux, relatively small, where at the upper inner target, they start already to be larger. So therefore, it might be better to consider what would happen when we increase the amount of EIRENE particles with a factor of 10. You, of course, have to keep in mind that this also will increase the computing time that you need. But when we look to it, then when we would do the same analysis, then you would not see on this picture the error bars anymore, as they are nearly negligible. So therefore, I chose here to increase the amount of IRENE particles with a factor of 10 and to continue with that for further analysis. And then that means that we can look to what is then on these bias corrected profiles, what we will find then as our discretization error. And that you can see here on these pictures. And there you can still see that they will still contribute a little bit, especially to the profiles of the particle flux and the density. And that you still have to keep them in mind, but that they are reasonable. So that means that our outcome of the simulations will not be completely wrong, but we still have to keep in mind that it might be a slightly difference just to the numerical errors. That's good for us to know, but it also means that this is not really causing the difference between the experiments and the simulations, which I showed you before. So therefore, I now come to the second part, and that is the sensitivity studies. So in the sensitivity studies, I basically modified some of the parameters, which were especially the upstream separator density, from which you can see here the effect at the right at the upper outer target, but also the input power, for instance, the anomalous transport in the divertor region, as it is set ad hoc in SOLPS-ITER. And you can see here, for instance, the effect from changing the upstream separator density. And you can see that by putting the upstream separator density down, that, for instance, my particle flux is also going down, which is more in agreement with the experimental data, but we are still far off. But at the same moment, you can see that the temperature agreement and also the heat flux agreement is worse as before. So therefore, these sensitivity studies will learn us a little bit about in which direction we can go, but it's clear that this is not really like the complete missing link of the physics which we should get. And that turned out to be drift effects. So drift effects are in SOLPS-ITER still challenging to include. That's also why they are not included by default in the solved equations. And this results, for instance, in the fact that you still have here some unphysical jumps in the simulation result, as you can see here, especially for the particle flux and the heat flux. And you could think that this is an artifact because these simulations are not yet fully converged, but they are fully converged. That is checked. The errors are also really small on them, but still they stay always over there. But nevertheless, it can learn us a lot that they are really required to get agreement with the experimental data, because you can see here the blue curve, that was what I get originally without drift effects, and now the red curve is what I get with these drift effects included. And you can see that here for the particle flux there is a huge improvement. The temperature peak is also shifting towards what we would expect from experimental data, and even for the particle flux it's still not yet completely what we would like to get, but it's already an improvement in comparison with what we had before. So therefore, at the moment, these simulations are taken as the best possible what we can get for the unseeded simulation to get. So therefore, the next step is to look a little bit better in detail, like what is happening in these simulations. And that's also for what I'm here now also looking to what is happening at the upper inner target. Because so far I was always talking about the upper outer target, as we have experimental data from the upper outer target. From the upper inner target, we do not have that. So now it might be interesting to see what's happening over there. And these simulations demonstrate that in order to simulate the asymmetry between the inner and the outer target, which is observed at many other tokamaks, for instance, at SDX upgrade, there was a huge study about it. You can see that without drifts, you have nearly a complete symmetry, as you can see here at the pictures for the density and for the temperature here on top. And here on the bottom, you can see the effect when we include these drifts, and you can see that here is a strong increased density at the upper inner target, and also that there the temperature is lower. The first question is then like, okay, when we have here already a lower temperature and an increased density, are we then maybe already in detachment at the upper inner target without that we have to add any seeding like I did with neon? But that seems not to be the case, because that I studied here with a density scan to see if we are already at the so-called rollover. But here you can see we are here, the operation point is here the most left point, and you can see that the density still should increase further in order to get at this rollover. So the conclusion is we are now in both an attached outer and inner divertor, And the goal is now to add this neon and then to see that we are indeed in detachment. For that, the next step is then to make these neon-seeded simulations. And that you can see here on the next slide. In these simulations, drifts are also completely activated, but I have to say that I had to change the anomalous transport, and I also had to change some of the boundary conditions in order to match the to get a reasonable agreement between the experiments and the simulations at the outer midplane and at the upper outer target. And as you can see already on these plots, you can see that the temperature is really low. So that indicates already that we are probably going towards detachment. But there is still one thing what you can say. You can say like, okay, here you still have temperatures of around 10 electron volts, which is normally slightly too high for being really in detachment. But when you look at the position where you have the peak in particle flux and the peak in heat flux, there you can see that the temperature is still lower. So that means that based on these simulations, we can conclude that we are in, that both targets are in detachment. And that you can also see when we look here to the 2D plots, then you can see that this asymmetry, which we had with drifts in the attached case, that this asymmetry is now much smaller when we have here this this neon-seeded case. You can still see that the density at the upper inner target is slightly higher and the temperature slightly lower, but you now have more again in this symmetric case. The interesting fact to know is then like, okay, we know that we have this neon, but where is it radiating? Because we want always to avoid that too much neon is radiating in the core, because that would mean that our fusion reaction is not going on anymore. And therefore you can see here on the right where we have most of the neon radiating. And this is around the X point. That's basically what we would like to have, because that's the place when we radiate over there, then we have the optimal choice of radiating at that position and still keeping a hot core. But you can also see that there is here still some radiation more to the bottom, and that's still currently something that is under investigation, what we are trying to find out what is happening over there, because this could be that it is really the case, and in that case we have to be careful with it, but it could also be that it is a kind of artifact from the simulation, as the grid is not extended up to the walls, but it is always only going 2.5 centimeters more or less further into the scrape-off layer. So that's basically still one of the last things on what I'm studying now. But for the rest, we can conclude already that it's clear from the simulations that this neon really brings both targets in detachment, and that was originally the goal to look to and to find out. So as a conclusion, I have that the goal was to achieve detachment employing neon seeding, and it was clear that the neon drives the discharge into detachment, and that was proven also together with the SOLPS-ITER simulations. And for these SOLPS-ITER simulations, it was then clear that the numerical errors could be kept reasonable by a good choice of the grid, applying the averaging mechanism in SOLPS-ITER and also including enough EIRENE particles. But I still want to point out again that it's really important when you have a numerical code and giving an interpretation to it, to first also have a look that you have not too high numerical errors. And secondly, it became clear that drifts are really required to match simulations and experiments, especially when you want to do that in a quantitative way. And with that, I would like to thank you for your attention, and I'm now open for questions.
Thank you very much for the very interesting and clear presentation. Now it's time for questions from George Wilkie. Please go ahead.
Hello, it was a very nice talk. Thank you. Can you go back to the slide that shows the effects of different proportions of drifts and the divertor footprint? Yeah, this one. Mm-hmm. Can you comment on why the heat flux footprint still doesn't get down to the experimental values?
I must say that's indeed a good question. That's still something which I must say I'm still currently looking to what could be the case. One of the what recently a collaborator of mine suggested was that this can be due to the fact that my grid is not extending too far, because they did before already simulations that was then with H2D EIRENE, which is a similar code at JET, and there they basically found that when your grid was not wide enough, that they had, especially for the power flux, that they estimated it too high. So that's one possible reason. Another reason can be the way how it is measured, that it might be that there are also still some errors on the measurement data, but to that, as I have not really access to the measurement data themselves, it's still that that might be a reason, but that I cannot investigate further. So that are basically the two options, that it might be that my grid is not far enough and that should be the case to match them, or that yeah, that the measurement data are not as we would like to have them.
Okay, thank you.
Thank you. I saw actually a response from Francis. I'm not mistaken.
Yes, yeah, I have a question. Yeah, thanks, Katia. Thanks, Dieter, for the talk. I have two questions. Like, one question is like the choice of the code that you use. Like, I think you used B2.5 and EIRENE for doing the simulation. Like, could you explain why did you use this code, this particular code for your work? And then the next question is, and how did you actually use the value of this anomalous coefficients for your simulation? Like, because B2.4, it's a fluid code, so we need to externally give this parameter. So how did you choose those values?
Okay, yeah. So first of all, why I chose SOLPS-ITER, the reason for that is mainly that you have at the moment several codes which are going in this direction, like Edge to the EIRENE, SOLPS-ITER, and so on. Why I chose SOLPS-ITER has partially to do with the people who were guiding me, that they had experience with that code, but also with the fact that that code was, at the time that I started, was starting to be able to to include drifts in a way, and made it in that way kind of one of the most complete code packages which I could use. You can also argue like, yeah, okay, you have other codes in 3D, but as this was a Tokamak experiment, it is computational less expensive to use than a 2D approximation, and you still get kind of good results. It's indeed true that it's a fluid code, so the B2.5 code is a fluid one. So for that, I used, that's one of my backup slides, basically, profiles, yeah, that you can see here now. So here on the right, you can see then which kind of anomalous transport coefficients that I used. It's basically, we know from experience that other people had who modeled similar kind of discharges. It is now an H mode discharge. Then we know that we have this transport barrier, which you can see here. And starting from kind of profiles of transport barriers from other codes, I just started to iterate my simulations till I had one of the most optimal agreements, which means, of course, that this is done kind of ad hoc. So it's not that we have at the moment already a strategy to really say like, that's exactly how it should go. But in that, when I had these profiles, I managed to get the best possible agreement I could manage between simulations and experiments. And that's basically how I came into there. But between the case without seeding and with neon seeding, you can see that I had to use a big difference in anomalous transport to get agreement between the simulations and experiments. So I hope with that, I kind of answer your question.
Yeah, thanks. Yeah.
Okay, thank you very much. I don't, okay, there is one more from Wieden, please.
Hello, Dieter. Thank you very much for this nice, concise, but very clear talk. I wrote a question in the chat, but probably you didn't see it. For this type of simulations, what is particular about East compared with other Tokamaks?
Oh, that's indeed that's interesting to think about. So the thing is, basically, then I have to start why we, for instance, chose to use East for these kind of experiments. That is that at the moment East has already upgraded the part to tungsten, but they use also a lot of lithium to cover their divertor. This has, for instance, as an advantage that they were at the time that I started to work on this topic, one of the only Tokamaks in the world who could deal with neon seeding and could basically investigate the effect of neon on what is happening in your plasma. But the disadvantage of that is also that this is not completely included in the code, because lithium is by default not one of the species that you can put in the EIRENE code to treat the neutrals. So I ignored, for instance, also this lithium completely, which makes that in comparison with, for instance, when you have experiments at SDX upgrade, there you have it full tungsten without lithium, your plasma is less dirty. So that's one of the differences that you will have. But for instance, when you look to the size of East, then it's really comparable to SDX upgrade. So therefore, the profiles that I show, for instance, here, for that I started from the experience that people had at SDX upgrade, and then went from that to East, but especially with this lithium wall, and also with the heating system that you are using, you have some differences between what we have here in SDX upgrade and what you have at the East Tokamak.
Thank you. Thank you.